In our previous chapter, we have discussed about discrete probability distribution, and in the discrete probability distribution, we have mainly discussed about the binomial distribution, and in the chapter, we have discussed about normal distribution, mainly normal distribution, right? And now we will see how we can use normal approximation to the binomial distribution. So here in this chapter, I have just put one main learning goal, and the main learning goal associated with this chapter is we will learn how we can convert the binomial probability distribution to normal probability distribution. So binomial probability distribution is a discrete probability distribution, right? We already discussed that in our previous chapter, and a normal distribution is a continuous probability distribution. So we will learn how we can convert the discrete probability distribution to a continuous probability distribution, and the discrete distribution that we are interested is binomial distribution, and the continuous distribution in that case would be normal distribution. So we will learn how we can convert a binomial probability distribution to a normal probability distribution. uh, just to look into the binomial probability distribution, because we have discussed that in our previous chapter, we might forget. So for a binomial probability distribution, we have n number of trials, right? The number of trials here is n, and out of n number of trials, we are interested to see how many number of successes, right? And we denote that by r, and in each trial, probability of success is denoted by p, and the probability of failure is denoted by q. Therefore q equal to 1 minus p, right? So this is basically the main things that you need to know for a binomial probability distribution. I hope like you all remember that. Now we have already mentioned, like, we'll be using normal approximation for the binomial distribution. Now the question is, like, when we can use normal approximation for binomial distribution. So the condition that has to satisfy, and in which situation we can use normal distribution instead of like binomial distribution, is those where n times p has to be greater than 5, where n is the number of trial and p is the probability of success in each trial, right? And in q also has to be greater than 5. So if both of them satisfy, then in the situation for the normal distribution we can use for the binomial distribution we can use normal approximation, right? And if the value of n is large, in that case, then the binomial probability distribution approaches to normal distribution. And if the value of n is large, then in that case the approximation gives us more accurate result, and we'll see that graphically in the next slide. So now let's see what happens when we have large n. So here, like, for all the four distributions, the original distribution for all of the four are binomial distribution, but for the first case we have n equal to 3, right? And for this case, what you can see, the distribution doesn't look like a normal distribution, right? But here for this distribution, everything else, all the parameter here that you can see are same like that, right? But in that case, only things that is different is the n. So here n is 10, and now you see the distribution for this is kind of look like normal distribution, right? And when the n is 25, then this distribution look like very much like a normal distribution. And when n equal to 50, then it look like a perfect symmetric normal distribution, right? So what you can see is that when the value of n is small, then the binomial distribution doesn't look like normal, but as the value of n increases, then the binomial distribution looks very much like a normal distribution, right? So therefore we can say, like, for large n we can use like normal distribution instead of binomial distribution, so we can approximate using the normal distribution, right? So let's now look into this problem. So here, what is the problem? Apartment building owner installed 25 quick hot water heaters, and probability that it will last 10 years is probability that it will last 10 years is with 0.25. Then what is success here? Then success is the water heater lasting at least for 10 years is the success here. So this is a binomial problem. The original problem is a binomial problem. Here n equal to 25, and probability that it will last for 10 years is 0.25, and success here is the definition of success in that case would be water heater lasting at least 10 years, right? So now the probability that we have to calculate in that case is what is the probability that 8 or more water heaters will last more than 10 years. And we can solve this problem by using the binomial distribution, since the original distribution was the binomial distribution. And we will see whether in that case we can also use normal approximation, and then we'll compare the two probabilities, like the binomial approximation probabilities and the binomial original binomial probability and the normal approximation probability, and we will see like whether they are very different or they are close. So here, what are the information we have? We have number of trial equal to 25, probability P equal to 0.25, and probability that the water heater will probability that at least 8 water heater will survive more than 10 years. That is the probability that we have to find. So now we have to first see whether we can use a normal approximation. So to use normal approximation, what are the condition we need to satisfy? We need to be NP has to be greater than 5, and NQ also has to be greater than 5, and in that case the N was 25, P is 0.25, so NP is 6.25, which is greater than 5, right? And NQ, N was 25, Q since like P is 0.25, therefore Q is 0.75, and therefore NQ is 18.775. Therefore in that case we can tell like N and P, both of them are greater than 5. So we can solve this problem by using normal approximation, right? And in that case, in the graph, so this is the probability we have to find, like this is the probability we have to find, that at least 8 water heater will survive more than 10 years. So here we have the 8, and this is the area we have to find by using the normal approximation, right? In the previous slide we have seen like in this situation we can use normal approximation, since NP and NQ, both of them was greater than 5, right? And so to use normal approximation, we need to first find the mean and standard deviation. And for the binomial distribution, what is the mean? So for the binomial distribution, for the mean, this is the formula that we have learned, right? For the mean we use NP, and for standard deviation we use a square root of NPQ. So in that case, therefore the mean would be in the value for N was 25 and P was 0.25. So NP would be 6.25, which is our mean. And what is the standard deviation? Standard deviation is the square root of NPQ, and square root of NPQ is 2.17, right? So this is the mean and standard deviation for this distribution. So we have seen like our original distribution was binomial distribution, but we will apply normal approximation in that case. But before applying the normal distribution, let's talk about another important thing, which is continuity correction. So our original distribution was binomial distribution, which was a discrete distribution, but we will be using normal distribution for the approximation, and normal distribution is a continuous distribution. And in that case we need some continuity correction. And how do we do that? So here our 8 was there, but if you look into this graph, this bar, then it basically started from like 7.5, right? 7.5. And so for what we do is that, for left endpoint, so for the left endpoint we subtract 0.5, we subtract 0.5 from the left endpoint, and our original point was say R was greater than or equal to 8, right? And if we subtract like 0.5 from there, then it is like 7.5, right? And for the right endpoint, what we do, and for the right endpoint, if we have right endpoint, then in that case we add 0.5. say if the original problem was like say probability that r is less than or equal to 8. In our case though it is greater than, but say if our original problem is probability that r is less than or equal to 8, then in that case for the continuity correction what we have to do, we have to add zero point 0.5 with this, right? And in that case for the continuous distribution, the probability would be that probability that x will be less than or equal to 8.5, right? I think now it is clear to you like what is continuity correction. So if it is a greater than problem, then in that case we have to subtract zero point 0.5. If it is a less than problem, that in that case we have to add zero point 0.5 with the original value, right? Therefore, our original probability in that case was probability that r is greater than or equal to 8, which was a binomial distribution, right? Now, if we convert that for the continuous distribution, then our problem is probability that x will be greater than or equal to 7.5, right? After the continuity correction. And now we have to find the corresponding g value associated with 7.5 raw score, and the g value is this, right? We know how to calculate the g score corresponding to this raw score. So it is 7.5, which is the raw score. Then the mean, we have calculated the mean, and the mean for this probability distribution was 6.25, and standard deviation was 2.17, right? So therefore the g score is 0.58, right, for this case. So in the previous slide, we have seen our g score value was 0.58. Therefore, the probability that we have to calculate is probability that g score is greater than or equal to 0.58. But since we are using only left table in the class, we have only discussed how to use the left table. So, but it is a right tail probability, right? Therefore, in that case, we cannot directly use that. So what we can do is that we know that this is same as 1 minus probability that g score would be less than 0.58, right? So now we can find this value by using the left g table. So what is the value then? What is the corresponding probability? 0.5 is here. Then we have to look for 0.08, right? And here it is 0.08. Therefore the value would be this one, this value, 0.71904, right? So this is the value that's associated with the g score 0.58. 0.5 is here and 0.08 is here. So this is the value that is associated with g score 0.58, right? So this is the value 0.7190, right? And 1 minus this value is 0.2810. So what would be the interpretation? Approximately 28% probability that more than 8 water heater or at least like 8 water heaters last for at least 10 years, right? So now let's see how we can solve this problem using the binomial distribution. So the original distribution of this problem was binomial distribution, right? And in that case the number of trial was 25, and we have to find this probability that r is at least 8, right? And now this is same as 1 minus probability that r would be less than or equal to 7, right? And from the binomial probability table, now we have to find this probability. So for the binomial probability table, for each n we have a separate table. So we have to look for a table where the n value is 25, and here those are the value for the probability for the different probability value. So in our case the value for the value of p was 25, if you remember. Like in that case the value of p was 25. So we have to then look this column. And what is r here? R is 7 here. So r is 7 here. Okay, here in the table they have denoted that as x, but that's same as r here. So here the r is 7, and then the probability that we are dealing is 0.25. Therefore the probability here would be 0.727, right, for the binomial distribution. So 0.727, and 1 minus 0.727 is 0.273, right? So this is the probability for that we find by using the binomial probability distribution. And now in the next slide we will compare the two probabilities the original probability that we calculate by using the binomial probability distribution, and the normal approximation that we have found by using the normal approximation, right? So now those are the values. So this is the probability value that we have found by using the normal approximation, and this is the exact probability that we have found by using the binomial probability distribution. And the difference between these two is just, very minute value. This is a very small value, right? So therefore you can tell that, like, when n is sufficiently large and when np and nq, both of them are greater than 5, then in that case we can successfully use the normal approximation, because the normal approximation value and the binomial exact value are very similar, right? The difference between these two is very minute, right? So to summarize what we have learned in this chapter, we have mainly discussed about, like, in which condition we can use normal approximation for the binomial probability, right? And the condition was like n has to be large and np and nq both has to be greater than 5. And then we have also learned how we can calculate the mean and standard deviation, right? The formula for mean was, for the binomial distribution, it was np, right? We have discussed that in our binomial probability distribution chapter, but we have also briefly discussed it here, right? So the formula for the calculation of mean for binomial distribution was n times p, and the formula for the standard deviation was square root of npq, right? That we have discussed. And we have also discussed, like, since binomial probability distribution was a discrete distribution and normal distribution is a continuous distribution, therefore to convert a binomial distribution to a normal distribution, we need to use some continuity correction, right? And we have also discussed, like, how we can do that.